Okay, we're now going to talk about the Diels-Alder reaction. This is a very important reaction. The scientist that discovered it, Diels-Alder, won the Nobel Prize for this. But it's an important reaction because it's another reaction where we form a carbon-carbon bond. In fact, we're going to form two carbon-carbon bonds, all right? So anytime we can form carbon-carbon bonds, we can build up reactions. So it's an important reaction because of that. All right. And it's another reason it's really important or interesting is because it's very useful. It's very simple. It's a very simple reaction. So we're first going to start with, we're going to have two reactants. We're going to start with a diene. Okay, we're going to start with a diene. That is going to react with an alkene. Okay, it's going to react with an alkene. And these two reactants combined, and we simply heat them up, right? So again, we can use a triangle. We heat them up, and they will undergo a reaction. In the Diels-Alder reaction, you always form a cyclohexene. You always form a cyclohexene. Okay, the product we form is a six-member ring with an alkene, a cyclohexene. Okay, very important to number your carbons here. Carbon 1, 2, 3, and 4. And then I'm going to label my alkene as A and B. Okay, so we always have a diene, a conjugated diene, and then we have an alkene. All right, and it turns out we have a special name for this alkene. It's called a dienophile. It's called a dienophile. All right. So this example I'm talking about here is just the basic reaction, right? It turns out when you run this reaction, generally speaking, it won't work with every diene and every alkene or dienophile, right? Your diene generally needs to be electron rich, and then your dienophile is generally electron poor. So it's not that every alkene and diene can react together. One has to be electron rich and one has to be electron poor. So you'll be seeing different groups coming off this for reactions that work. You can have inverse demand where your diene is electron poor and your dienophile is electron rich. But generally speaking, your diene will be electron rich and your dienophile will be electron poor. Okay? But generally speaking, I will be giving you Diels-Alder reactions that work, so that's not something we have to worry about as much. All right? So in this reaction, right, 1, 2, 3, and 4, there's A and B. What we're going to see is we're forming two new carbon bonds, a new carbon bond between 1 and A, and a new carbon bond between 4 and B. Okay, and for this reaction, I always recommend numbering your carbons, 1, 2, 3, and 4, and A and B. It really helps you figure out how to do the mechanism of the reaction. All right, let's draw the mechanism for this reaction. It's actually quite simple. Again, we will number these, carbon 1, 2, 3, and 4, A and B. To get this to work, you just heat them up. So I'm going to draw the mechanism, and here's what happens. Okay, the double bond between 1 and 2 is going to form our new single bond between 1 and A. This double bond between A and B, the two electrons from that pi bond, are going to form our single sigma bond between B and 4. And then the double bond between 3 and 4 moves to become between 2 and 3. So you can draw your arrows sort of in a clockwise or counterclockwise fashion. It doesn't matter. Okay? Double bond between 1 and 2 is forming a sigma bond between 1 and A. Double bond between A and B is forming a sigma single bond between B and 4. And the double bond between 3 and 4 is now forming a double bond between carbons 2 and 3. So let's see what that looks like. Again, we always draw our cyclohexene. carbon 1, 2, 3, and 4, A and B. Carbon A was connected to a random R group. This double bond here has now formed that single bond between 1 and A. This double bond here has formed my sigma bond between B and 4, and the double bond here has moved between 2 and 3, right? So we're always going to form our 6-membered cyclohexene ring, right? This is what it looks like. So that's the basic reaction. It's a one-step mechanism. You push 3 arrows at a time. Okay, very, very simple. But it's important that you draw the molecule the right way to do the mechanism. All right, so that's the reaction. What we want to do now is just look at some examples of this, okay? So here I'm going to take a diene, all right? Notice now instead of drawing 2 reactants, I'm going to draw 1 carbon chain as a reagent. All right, so what I'm going to do here is now draw my alkene. I'll make this a ketone, all right? And then we heat the reaction to get this to work. So what is the product formed here, all right? Got to identify our diene, carbon 1, 2, 3, and 4. Identify our alkene, our dienophile A and B. Now let's redraw them so I can draw the mechanism. Notice here that I've drawn this in kind of like a transoid configuration, right? So when we draw the mechanism, I need to rotate this out so we have our diene in our cis-oid conformation. So really what I'm doing here is I'm just rotating the bond between carbons 2 and 3, so my double bond, the double bonds at the end are at the same side. Okay, so we always have to draw our diene kind of wrapped around itself. We call this the cis-oid conformation. We then draw in our alkene. It doesn't matter if A is at the top or B is at the bottom, so you can switch these, it doesn't matter. So I'm now going to redraw this, right? And it's important for us to notice here, right, that this is E or trans. Okay, so my methyl and my ketone are trans to each other, and I've drawn that here because that's going to be important. And then we label A and B. To draw the mechanism, the double bond between carbon 1 and 2 forms the single bond between 1 and A. The pi bond between A and B forms my sigma bond, my single bond between B and 4. And then the double bond, the pi bond between 3 and 4 goes to 2 and 3. So what does that product look like? We always draw a cyclohexene. 1, 2, 3, 4, A and B. And now what I want to show you here, right? The methyl and the ketone were trans, right? They were trans or E, which means in our product, they have to be anti. They have to be on the opposite side. So carbon A was connected to a methyl. I'm going to draw in some stereochemistry. Here's my methyl. I drew that as a wedge, which means the ketone now has to be a dash, right? A was connected to a methyl. Methyl. B is connected to our C double bond O methyl, our ketone. These have to have opposite stereochemistry. Trans always becomes anti. Okay? So it's just important to know one has to be a wedge, one has to be a dash, and it's okay if this was a dash and that was a wedge. They just have to be opposite. All right? Let's look at another example here. Now I'm going to take a diene that is part of a ring. I'm going to react this with a dienophile, an alkene. I mix these two together in some solvent, right? So sometimes you might see a solvent listed here. But what's important is that you're also going to see heat, right? A triangle means you have heat. So now let's figure out what our product is going to be, right? I'm going to redraw my diene always the same way here, right? But notice that this is a ring, so I've got to draw that ring as such. I label my carbons 1, 2, 3, 4. Now we have a carbon 5. I'm going to redraw my alkene. What we should notice here is in my alkene, the aldehyde and the chlorine are on the same side. They're cis. So what do you think that's going to mean in our product? Trans or E means anti. Cis, it means that these are now going to be syn. Let's redraw this molecule here. We'll add our chlorine. We'll add our aldehyde. Okay, so I'm redrawing these molecules to fit the format. We know 1 will form a bond to A, 4 will form a bond to B, right? If I don't ask you to draw the mechanism, you don't have to. The pi bond moves from 1 to 2 to form the single sigma bond from 1 to A. The double bond from A to B forms my single sigma bond from 4 to B, and that double bond moves between 2 and 3. Let's draw our product. Watch how I draw this. I always draw my cyclohexene. Always draw a cyclohexene. Carbon 1, 2, 3, 4, A and B. Okay? But remember, 1 and 4 were connected by carbon 5. I've got to draw that in. There's my carbon 5, right? I just draw that right in the molecule. A was attached to a chlorine, B was attached to an aldehyde. These were on the same side cis, which means they have to be syn. I've got to draw these as both dashes or both wedges. A is connected to a chlorine, B is connected to an aldehyde, and this is the product that we form. So here I've drawn this molecule. This is my 2D drawing. Okay, that's my 2D drawing. This is a bicyclo compound. So I'm now going to just draw what this looks like in 3D. Okay, this is the 3D representation of what this looks like. I'm showing my Cl and my aldehyde are up on the same side, right? So you may see some 3D drawings of this. Carbon 1, 2, 3, 4, 5, and A and B, okay? But, you know, if you're not comfortable sort of drawing our 3D model here, it's fine. You can just draw the 2D version of what this looks like, right? Easy for you to draw the 2D version of this, all right? So that's the Diels-Alder reaction, okay? Pretty straightforward. Right? Again, really focus on identifying 1, 2, 3, 4, A and B. Draw your cyclohexene 1, 2, 3, 4, A and B. If this happens to be a ring with carbon 5, just include it in there. Simple. You still have your cyclohexene shown here. And then we have to remember if your two groups are trans to each other, they have to be anti. If they're cis, they have to be syn. So that's the basics of the Diels-Alder reaction.